Okay, so what are the stages in structural equation modeling? The first stage is called as model specification, which is very clear. Okay, we have to specify the model, right? We were talking about in the introduction also that this is a confirmatory approach to model testing. So you will have to specify the model, right? Then we come to identification, which is where we will be computing degrees of freedom of the model, and the degrees of freedom should always be greater than 0. Ideally, it should be greater than 0. If it is equal to 0, you will be able to get the estimates, but you will not be able to get the model fit indices. Then the estimation methods, there are different kinds of estimation methods. Then there is going to be model testing, and where we'll talk about the fit indices of the model, whether the model is good or bad. Okay, those kinds of details are looked at. And then finally, model modification. How do you improve the fit of your models? Okay. So let me go through each one of these steps in detail. So model specification is the exercise of formally stating your model. What are your constructs? What are the measures of these constructs? Okay, and how these constructs are going to be related. All of this is basically derived from theory. Okay, it has to be based on theory, and there is no quantitative analysis here, right? So a lot of people ask me, well, will the data tell me what constructs should be related? No, that is not what the software is intended to. The software is intended to test the relationships that you have specified. The software cannot recommend what relationships should be specified. Yes, more software can tell you some incremental improvements, right? But it cannot tell you what paths you should do. Ideally, you need to build it based on your reading of the literature, understanding of the theory, and so on. And there could be misspecified models. If you miss out some variables, you include variables that are not important. Well, that is all based on the theoretical models that you are working on. So the first step is actually not SEM based step, which is clearly defining what is going to be your model on which you are going to test these or run the software. Okay, so now there are some rules. We will come to, yeah. So let me just take you through these steps, but we will again come to this when we actually do our CFA example. So there should be, for each latent variable, there should be a metric of the scale that needs to be set. So for any independent, any latent variable, it is not just independent, any latent variable, one path leaving the latent variable has to be set to 1. So if we were to go back to this picture, this diagram, you should ask, why is this path constrained to 1? Okay, that should be a logical question that should come to your mind. Why did we need to constrain this path to 1? And the reason to do that is, well, you need to do this because this is a latent factor, right? We have collected data on pre-send and pre-op, right? These were two observed variables, the two rectangles here. So I knew that this data is collected on a scale of 1 to 5. This data is also collected on a scale of 1 to 5 or 1 to 7, whatever scale you have for your data, for your item. But the software is trying to estimate this latent factor, and it does not know what should be the scale. What should be the scale for this particular latent factor? Should it be 1 to 5? Should it be 1 to 7? Should it be 1 to 10? Should it be 1 to 100? Right? So in order to do this, we need to specify to the software one for a path. That means this one indicates that the scale of pre-SEM, if it was 1 to 5, will also be the scale for verbal, pre-verbal. That means now the range for this latent factor is going to be between 1 and 5. Similarly, there is another latent factor. So there should be at least one path leaving this oval that should be constrained to 1. Now, it is absolutely up to you whether you constrain this or you constrain the second path. It is your choice. No, there is nothing right or wrong here. You can constrain this path also. You can constrain this first path also. It is absolutely your decision. But the point is you will have to constrain one path. The second thing is all the errors that you measurement errors, all the paths from this oval to this rectangle, they are all constrained to one, which means or which implies that this measurement error is only associated with this item and not with other items, which is actually quite logical and intuitive that this is a measurement error associated with this item, and so it is logical to say that, well, this coefficient is 1. Similarly, this structural error is associated with this latent factor, and therefore its path is constrained to 1. Right? So these are 2 or 3 rules that you will need to keep in mind. At least one path, not at least uh, any one of the paths, okay, leaving the latent factor must be constrained to 1. All the error paths are constrained to 1. Okay, so this is the rule, okay, and paths leaving from the error terms to their corresponding observed or latent variables are assumed to be equal to 1. Now let us come to the second part, which is the model identification part. Okay, and this is where we talk about the degrees of freedom of our model. Okay, so what is the degree of freedom? So remember, we had said that we are going to test this hypothesis when we will be testing whether our model is good or not. We said we will be testing this hypothesis chi-square for degrees of freedom is equal to 0, or chi-square for degrees of freedom is greater than 0, right? So this is what we had assumed, we had stated. Now, chi-square is okay. Chi-square is, you get an estimate of the chi-square from the, uh, we multiply n minus 1 with the S minus sigma matrix, right? So it gives you a, this is roughly the formula of, there are some weights also attached. Okay, so we also have some weights that are attached to this. So it's a weighted matrix, and then we multiply it with n minus 1, the sample size minus 1. Okay, so to get an estimate of chi-square. But how do you compute degrees of freedom for the model? Now, degrees of freedom are computed by this formula. We say k plus 1 by 2 minus hash theta, right? So this is the formula for computing degrees of freedom in the model, where k is the number of items and hash theta is the number of parameters to be estimated. Okay, so now let us look at an example to see what this means. So let's say we have a factor like this. Okay, we have 4 items, I1, I2, I3, I4, and we have the 4 measurement errors. Okay, and one of the paths is always constrained to 1. This is what we have seen. Now, what will be K here? K is equal to the number of items, which is 4. So, what is K? K plus 1 by 2? It is 4 into 5 divided by 2, which is 10. What is hash theta? Hash theta is the number of parameters. So we have already looked at it. So we said factor loading. So number of factor loadings, number of measurement error variances. Then we said number of structural paths to be estimated. Then we said number of structural error variances. Then we said number of covariances, and we said number of independent factor latent factor variances. So what is theta, hash theta here? Let us look at it. How many factor loadings? The factor loadings are 3. 1, lambda 1, lambda 2, and lambda 3. How many measurement errors? So there are 4. So therefore, there will be 4 measurement error variances that will be computed. How many structural paths? At this time, there is no structural path because it is just one factor. So it is 0. How many structural error variances? 0 because there is no structural path, right? How many covariances? At this time, there is no double direction arrow that we see in this diagram, 0. And how many independent latent factors? So we have 1. So it becomes 8. So what is our degree of freedom? It becomes 10 minus 8, which is 2. So in our models, we always say that degree of freedom should be greater than 0. This condition is called as over-identified models. Only if you will have greater than 0, that is only then can you test this equation. Otherwise, you cannot test this equation because there is no chi-square distribution for a df is equal to 0. Right? So that is 1. Now let us take another example. Everybody, okay, pick up your pen and your a piece of paper. Let us compute the degree of freedom of this model now. Okay, do it in your notebooks before we discuss. Okay. Right. So this is what going to be our degree of freedom. Okay. So k is equal to 3. So k plus 1 by 2 is equal to 6. Hash theta, we know it's all of this. So there are 2 factor loadings. There are 3 measurement errors. Okay. Then there are no structural path, no structural errors, no covariances, and there is one independent latent factor. So theta is 6, and therefore degree of freedom is 0. This is called as a just identified model. Okay, so the software will give you the parameter estimates, but you will not be able to test this hypothesis. So you will not be able to test the goodness of fit of fit of your model in this case, right? So this is called as, and this is one reason why you see we always recommend that ideally you should have 4 or more items for each latent factor, else at least you should keep 3 or more items. So at least keep 3, or you may keep more than 3 items in your latent, measuring each latent factor, right? Just do one more example and then I will take questions. Just quickly do one more example. This should be a cakewalk now. What will be the degree of freedom? Okay, so it is k plus 1 by 2 minus hash theta. Everybody do it in your notebook. I'm giving you 1 minute before I start writing. Don't tell the answer, just solve it in your notebooks. One of this path is going to be tied to 1 as always. So this is no exception. So one path is going to be tied to 1. K is equal to 2 here. So k plus 1 by 2 is equal to 3, right? Now, what is hash theta? Number of factor loadings, 1. Number of measurement errors, 2. Number of structural paths, 0. Number of structural errors, 0. Number of covariances, 0. And number of independent latent factors is 1. So you have degree of freedom as 3 minus 4 is equal to minus 1. This condition is called as an under-identified condition, or your model is under-identified and the software will give you an error and it will stop. It will say, I cannot do it because you need to maybe put some constraints somewhere in order to reduce the number of parameters that I have to compute. So if I constrain this one also, then my factor loadings will become 0. Okay. In that case, my hash theta would become 3 and my df will become 0. So the software will give you this error saying that you need to impose some constraint, at least one more constraint, in order to make the degree of freedom 0. Otherwise, if it is an under-identified model, the software is not going to solve the model and it will not give you any result.